Hello, let's continue our Sudoku adventure with Two Ways by PjoeterBliep. So we have normal 6x6 Sudoku rules. That means in each row, each column, and each 2x3 box, we are placing the digits 1 to 6 exactly once each. We also have these blue lines in the grid. These are called region sum lines. Region is just another name for a box. So the way these work is as we cross a box boundary, we create a new segment on the line. So we're segmenting the line based on box boundaries. So we could call this the green segment, the purple segment, and the orange segment. So you'll notice that this is a 2-cell segment, a 2-cell segment, and a 1-cell segment. On the same line, every segment has the same sum. So in this case, whatever this digit is, say it was a 5, that would mean that these two sum to 5, maybe a 2, 3, and these two sum to 5, maybe a 1, 4. So this would be one way to fulfill this line. But just because this line adds to 5 doesn't mean the other lines add to 5. Each line can have its own sum. It's just the segments within the line have the same sum. And that is it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. Okay, so my example kind of tipped off a few things we're going to be looking for in this puzzle, but all of them have something interesting, so it doesn't really matter. This can only be 5 or 6. Imagine if it was a 4. The problem is that this would have to be a 1-3 pair because it's the only way to add to 4 without repeating, which we can't because it's in the same box. One thing that's nice about region sum lines is there's kind of an implicit non-repeat within the segments because the segments are divided by the box borders, so they're by definition in the same box. This seems fine, but this would also have to be a 1-3. The problem is that this cell is affected by this pair, meaning that this can't be the same pair. And so we need two different ways to do the sum, and the only 5 and 6 have two different ways to sum to them. So the 5 is going to be 1, 4, or 2, 3, and the 6 is going to be 1, 5, or 2, 4. We don't really know. This has the same exact issue. It's completely symmetric. So this is 5, 6 as well. So one of these is going to add to 5. The other is going to add to 6. Now, whatever this digit is, it's cloned here. These are the same digit as each other. So I'm going to just use green to remind myself of that. These are the same digit. If this ends up a 3, that's also a 3. This is a 4, that's also a 4, right? Same sum. And then this is how we add to it. We know that's going to be from 3, 4, 5, 6, but not much else. And it's at this point I express surprise that this puzzle solves uniquely. I'm sure it does. It seems fairly minimal, which is a neat find from PjoeterBliep. So it probably has to do with this box. Why do I say this box? Because it's got 4 cells involved in 2 different sums. So sometimes it helps to combine. So for example, one thing we can think about is what is the absolute minimum that these 4 cells can add to? Well, they could be 1, 2, 3, 4. This can add to 5. This would add to 5 in that case. Ooh, that's interesting. Okay. Ooh, that's it. So let me give the original argument, and then I'm going to refine it a little bit. So the original argument is these sum to a minimum of 10, which means these sum to a minimum of 10. Why? Because they're the same sum. This is the same as these two, and this is the same sum as these two. So if we sum these two, it's the same sum as these 4. So the absolute minimum this can add to is 10. So this can't be a 3, which means that's not a 3. Oh, this has the same thing. No, this is a different sum. But these are cloned, so this is also not 3. But there's an interesting argument here to refine this a bit, which is that if this was a 1, 4 or a 2, 3, oh no, 2, 4 can add to 6. I completely missed that. And so that's what would have to happen, right? No, because these can add to 6. One of these would be 5. Would we do 4, 6? Yeah, we could do 4. Anyway, sorry. There's not really a way to refine that. But I will note that these add to a maximum of 11. So I guess one thing to say is these 4 cells add to a minimum of 10, and they add to a maximum of 11 because the smallest these can be is 10, and the biggest these can be is 11, 5, 6 pair. So 10 or 11 is very restrictive. 10 is 1, 2, 3, 4. And 11 is 1, 2, 3, 5. So the point here is that if these add to 10, there's a 5, 6 pair that's left. That's interesting. Let's think about that. But the other thing, let's just to finish that thought. If these add to 11, then it's the 4, 6 pair that's remaining. So these are from 4, 5, 6. So maybe that's kind of what I was seeing is we make a 4, 5, 6 triple here. but I'm a little bit worried about that. So if these add to 10, this is a 5-6 pair. That makes this a 5-6 pair, which makes this a 4, and then this actually has to be 6. And that I think that's kind of what I observed earlier anyway. Okay. So 4, 5, 6 triple means that this is a 1, 2, 3 triple. Let's use what we can find here. Huh. What else can I do here? There are other ways to combine sums. We could look at this. This adds to the same thing as this. So it adds to 10 or 11. Not really. I don't think that's really going to do much for me. Okay, what else am I missing? These are 1, 2, 3, 4. I've been, because of the 5, 6 pair, but I've been reluctant to pencil that. So these are the green 4, 5, 6. We might as well give a color to the rest of them. So we'll call this the purple 4, 5, 6 and the orange 4, 5, 6. We know purple's not 4. But we could color our 4, 5, 6 triple in this column, knowing that they're all different digits. And this we can then observe, actually this is helpful, can't be green and can't be purple. So if it's not green or purple, the only option is for it to be orange. And that means that the only color that can be 4 is green. So this is actually 4, and that makes this a 1, 3 pair. If this is 4, the maximum this can add to is 10, and that makes this a 2, 4 pair. So this is our 5, this is our 6. Okay, that's a 5. So the coloring worked. That was neat. So this adds to 6, and remember it had to be 2 different ways to add to 6. This can't be 2 or 4, so we're down to just being 1, 5 here. So that can't be a 1. And we're down to 2, 3, 6 here, and the 6 is placed right there in the box. And this is 2, 3. Oops, this is 2, 2, 3. Okay. All right, that was fun. So 5 somewhere down here, 6 is over here. What am I missing? Oh, well, this adds to 5. So we know that this is going to be from 1, 2, 3, 4. And this doesn't involve the 4. So this has to be the 2, 3 way to add to 5. This is the 1, 4 way to add to 5. Because again, a 2, 3 would have too many 2, 3s in this column. So 5's up here somewhere, 6 is down here somewhere. Oh, 5 is actually placed. Okay, that's our 5. 5 is placed in this box, giving us the 1, 5 here. That gives us 3, 2, and 3, and 1. Giving us the 4 and 1 and the 3 and the 2. That's our 2. That's 2 and 4. Wow. Okay, I think it's just Sudoku because all the lines are filled. This is a 3. Over here we need a 6 and a 2. Up here we need a 1 and a 6. Okay. How about these pairs? This is a 1, 3 pair. This is a 4, 5 pair. We know the order. That's 4. That's 5. Well, this is just a 1, giving us 3 and 1. Okay, so up here we need a 2 and a 3. That's 3, that's 2. Down here we need a 4 and a 6. That's 4, that's 6. All right, neat find there, PjoeterBliep. I really liked these interactions, and then the coloring of the triple seemed to be key. The fact that this couldn't be this digit or this digit, so it had to be this one. You can kind of just see that through the column, through this medium, but the coloring helped me see that. Very neat. Let me know how you did, and if you enjoyed this, want to leave a like, subscribe, and a kind comment below.